So I'm recording this because I don't know. I thought I could. It's okay. Well, anyway, so some time ago, there's this. If you look, there's sine times the arc cosine of x, and because there's a trig function and then an inverse trig function or uh like a reverse trig function, an arc function, whatever. It can be represented algebraically. Okay. And if you take a look, all the way here, um, like like this, yeah. Let me. Okay. Basically, it looks like this for the first one, and then if you do the second one, it looks like this. Oh, but this is adjusted, yeah, 0.5. And this is 1/3 here. If you don't, everything is just in between 1 and -1. This is multiplied by 1/3 here to make it spread out 3 times and stuff. And what this does basically is as you increase the number of terms, like if you go for example 8, right? Okay, this looks pretty similar to negative sine of x, right? And yeah, so as you approach 0, it gets closer and closer. Like if you look here, you can see that it's starting to spread apart. And if you zoom really close, you can tell that these aren't. But as you approach 0, it gets closer and closer together, sort of thing. So it's similar in essence to the Taylor expansion series. I tested scaling it different ways, and with this combination, yeah, it approximates it pretty well, close to 0. Arguably, it's not as good as Taylor expansion series, but you know, I thought it might be easier to compute, maybe. But probably not. Okay, anyway, so what I'm doing here, so getting a pretty good approximation of sine function or any trig function can be pretty good. So what I decided to do was do a little bit of data collecting. Dude, so basically, yeah. So on this notebook here, I studied it a little bit, and I came up with sort of a rule for it. Which, I mean, honestly, I don't even use this rule because that's like for each specific term. There's actually a formula for each like tau. That's like called each of the things. Like the first tau, it's represented as t to the power of t, like small t minus 1, which is this number here. And the lower one right here, so like the functions, let me see here, these ones, they're the ones that show you what it is, and there's a pattern to it, which is reflective here. You can actually derive that from here, but anyway, I started collecting it, so I realized I was doing it wrong, and I was, you know what, at this point I wasn't gonna write everything down. It was taking a while. So I was doing this. I've been collecting the data here. So I'll kind of show you the process, okay? So we're at 40. We actually jumped quite a lot. Like, if you take a look, all of this, so at around 8 or this is closer to 9 on the line here. This is when we peaked, and we slowly started to descend the numbers. First, we were going like not that much in terms of like in comparison to the number. So went from like 5, around 6 to 4, then to 2, then to 1 and stuff. And then from here we were descending, and then yeah, as you approach here, you're descending about 1 decimal every time here. But then we just had a massive jump, kind of. We jumped like 2 or 3 orders of magnitude. And I'm nearing the end, or I'm sensing that I'm nearing the end. We have about 10 terms left or so, I think. So yeah, basically 41, and this gets multiplied by, nope, 18 and 19. Go here. Now 17, we're nearing the end, yeah. 59, goodbye. And this gets you 25 quintillion. So, wait, were we? Yeah. We're losing decimals really quickly. Pretty quickly approaching 0. Yeah. Okay. Yeah, so I guess I'll be back when I'm done, I guess. Yeah, it would help if I knew how to do math. Okay. I think with this... Oh, it's 100. It's pretty cool, actually. It's also quite a drop. That should be the end, because... Yup. This is the 50th term, since we start at 0 factorial, and then we enter 50. This becomes 0, and because everything's being multiplied to each other, this 1 honestly doesn't matter. And obviously if you wanted to continue, this would be -1, but it doesn't matter, everything's multiplied by 0. And below this, it's still gonna exceed standard computation time, I think. Hope you can... Yep. Alright. So with this, we're officially ready to try to graph this. I'll be using M, or I'll be using N. So I'll fix this to be 1. So that's, okay, it's going to be a little bit of a pain. A little bit. Okay. Control C, and I'll put X in the front when I'm done using this. V, X to the power of 99, yep. 99. K. Oh my gosh. Oh, it's so close to undefined that it doesn't even show up. It's actually pretty funny. Okay. Alright, I'll try graphing this and then I'll be back. Some update, I'm still going. Past the halfway point, and we're... So, okay, kind of for the procedure, so this here is the n to the 43rd power k, and then here's a minus. So the signs flip each time, and the power is actually decreases by 2 each time, so this would be n to the 41st, and then it's going to be plus. So I'm going to paste this, and to the power of 41k plus, I think that was minus, right? Yeah. Okay. So 43 minus 41 plus, so here. It's starting to glitch a little bit. I'm wondering if Desmos even has a character limit at this point. This is a lot. This is definitely way past Wolfram Alpha's character limit. But Desmos is still graphing, and it's not graphing the same thing over and over again. So I'm actually kind of impressed with the amount that Desmos is able to deal with. Okay, and then minus, right? Minus plus. This is 41 and that's 39. Yeah. Minus. Yes. Plus minus. Okay, whatever. Okay. Yeah. So I'll try to finish this. Okay. I did manage to finish it. There were a couple of mistakes I made along the way, and that ended up taking a lot of time and effort. You see me labeled everything here. I accidentally skipped 71. Yeah, this number 8977714. This one. And yeah, it was a lot of pain to fix everything, but I managed to do it. It seems to predict very, very well. Like, if you do just around 20 terms or so, by the time it gets to like pi, or well, I guess a bit, yeah, like past 2 pi, or no, 2 pi would be here. Well, like 4 or 3/2 pi, right? That would be here. Usually, like, you can tell it's not even close. But this seems to predict it very well. Now, at around, around past 10, it does start to get a little bit, but in terms of accuracy towards 0, it's very close. Now, I think Desmos came to a breaking point because, yeah, it struggles a little bit here. It's not supposed to look like this. Yeah, it just looks like a black blob. I don't know if it would fix if I zoom in. Yeah. If I would have this at just 1, it would actually struggle. Wow. Yeah. Not exactly what it's supposed to look like. It does take a while to graph. Oh, that was quick. If I change this to, for example, here's what it's supposed to look like. Yeah. Let me at if m would be just 1. Let me change this to 1. But let's see. It doesn't exactly look like this. Yeah, it's very close right here. But for some reason it's like this. I'm assuming this has to do with Desmos not being able to graph it at this extreme huge numbers, because this goes to like on decillions, these biggest terms. So I'm assuming it's just that the Desmos can't handle it or something. But yeah, now I can use this. It's technically not a polynomial because it uses this, which is a fractional exponent, kind of, or like you can't express it in terms of just, I don't know. But yeah, it is algebraic, so I'm sure this will come useful if I want to do something related to pi, maybe. I don't know. It's going to be hard. I want to calculate, like compute the value of pi using this, but because this isn't a 1-to-1 function, it's not going to be exactly clear how to do that. Yeah. Yeah. Okay.